Today I'm going to talk to you about basic validation in Polkadot. So last time we talked, when we were talking about Polkadot, we talked about the Merkle tree. So the state of the parachange is stored in this Merkle tree that we discussed. Um, in the Polkadot documentation, they talk about the leaves of for example, are a token balance and a person, and they're hashed and appended to adjacent leaves until you get to the root. Now, the interesting thing about a Merkle tree is that the property, if a value changes, it can be verified by looking at the new value and the path it affects. And I suspect we'll see when we actually start delving into actually using, on an actual instance of a Polkadot blockchain. Now let's talk about block state. The block is a list of state transitions. Example, paying to another wallet. Polkadot validation, it focuses on state transitions, not the state itself. So it's not looking at the, you may have the state, which is, what's in each person's wallet. It focuses on the transitions. The example I came up with on this is baseball, right? Baseball, you have, of course, home plate, but then you have the three bases. And your runners on, the state of runners on base can have 8 states. 2, either runners there or they're not, to the third, 3 bases. So state 1 might be no runners on base, state 2 must run on first, runner on second, runner on third, runner on first and second, second and third, first and third are bases loaded. Those are the only states of the state of the base path, I guess, that you can have in baseball. So, continuing this analogy, if all the runners moved or called out according to the rules of baseball, we know the base paths are in a valid state. Thus, if all the plays were valid plays as validated by the umpires during an inning, the state of the base paths are valid. So this is analogous to the blockchain. If the transitions are validated such that 2/3 of the validators agree they're valid, then they're valid. Once this is done, the information for the relay chain, the candidate receipt is created. So the idea is you create a block of information of fixed size that you can pass to the relay chain to show the information that it's valid. Now, erasure cutting is something interesting. It allows the block to be reconstructed by 1/3 of the nodes. So the parachain block in proof of validity, it's turned into a message, and it's chunked. So each validator gets part of the chunk, gets a chunk, and it's done so that only 1/3 are needed to recreate the message. In their documentation, they explain that, let's say a collator creates a valid block and then shuts down. Now, without this, you have no way of validating the chains because you need whatever, they created the block, whatever information. But the other nodes in this case can still validate because it's already created the chunks of the message enough that if you only need 1/3 of them to validate to reconstruct the message so that it can continue on. Now this is an example of a candidate receipt, and again from their website. I basically took their list and put in a little block. So you have the parachain ID, the collator's ID and signature, a hash of the parent's value, the parent block's candidate receipt, the Merkle tree root of the block erasure coding. So that would be that Merkle tree we talked about of, let's see. So the erasure coding is a Merkle tree. I don't know if and this is the Merkle tree, the root of any outgoing messages. Then there's a hash from the block, the state root of the parachain before block execution, and the state root of the parachain after block execution. And this represents a validation proof by using either hashes or numbers. So the parachain ID is a number, collator's ID and signature. Now the signature may be a hash. The hash of the parent block's candidate receipt. A Merkle tree root, which again is a fixed piece of size. A Merkle tree root of any outgoing messages, again a fixed size. The hash period from the block itself, again a fixed size. The state root of the parachain before block execution, again fixed size, and the state root of the parachain after block execution, which is a fixed size. So as you can see, this block or this receipt is going to be a fixed size, which in terms of scalability, that makes it much, much easier to scale because you're not creating data of unknown size. You have this fixed size candidate receipt. So this was a brief introduction to validation, and we're going to take it from there. There's a lot more to discuss theoretically in terms of we haven't even gotten into some of the I think Grandpa and Babe, which are two key algorithms in Polkadot. I think Grandpa, I think it's the validation. Babe is the mining. And we also have not, well, I showed you where the code was yesterday on my previous video, where you can find the code for Polkadot. We have not yet put it on, installed it, and gotten to that. But that's definitely on the agenda. I think once that is done, I think things will become even clearer because you can actually see the blockchain operating. So anyway, that's all for today, and thank you very much. Take care.